Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'd like to welcome Luca Borgo, which is here for an interview for a postdoc position in constraint satisfaction. So he's going to give a high-level overview of the field, and he will present some of his contribution in specific domain propagation. Thank you.
Thank you. So I hope it's working. Yeah. Well, thank you very much to Youssef and to the people which made it possible for me to come here to this talk. So yeah, it's going to be broad because I'm expected people would have different backgrounds. So it's somewhat introductory to this kind of things and centered on propagation techniques specifically to solve constraint satisfaction problems. And I will try to highlight some personal viewpoints and contributions. So I come from the Dipartimento di Informatica e Sistemistica in Rome, Italy. So the talk will have, just let me say before that, feel free to interrupt me if you want, if something is not clear during the talk, which might happen. So I will introduce you to these constraint satisfaction problems, and then talk about the specific technique to solve them, on which I'm interested, propagation, and then discuss a bit on applications and perspectives. So let's start with constraint satisfaction problems, and problem, and then the algorithms, the state of the art. So the problem I'm interested in is CSP for constraint satisfaction problems. Not the CSP some of you might be interested in. So with CSP, this is a form of what I would call broadly computer-aided decision-making and problem solving. So this is a thing where you model a real-life problem into some formal mathematical form, say, and you use a computer to find solutions or optimal solutions, these kind of things. And more specifically, constraint satisfaction problem is you model problems using variables and constraints on these variables, and you want to assign values to some variables so as to satisfy these constraints. It is a broad definition depending on what kind of constraints you have, of course, and what kind of values, domains for the variables. So just to give you an introductory example and something on which there is some hype recently in the artificial intelligence field, I wanted to start with this example on game theory, some basic game theory. So in game theory, if some of you know of it, you have different people which have different opportunities. For instance, there's you and there's a competitor, say. And you have, for instance, 3 possible decisions to make, like A, B, C, and the guy in front can make the choices alpha or beta or gamma. And the outcome you're going to have depends on both choices. For instance, if you make decision A and the competitor makes decision alpha, you're going to win, say, 65 pounds. If it's A and the other takes beta, you're going to win 40 pounds. So usually the problem is they consider in this kind of game theory is to assign probability distributions to all these choices. So you have to fix what probability you're going to assign to A, to B, and to C. So, well, you have variables for A, B, C, alpha, beta, gamma. They range over 0, 1 since it's a probability distribution. And of course, since it's a probability, they sum to 1, both for you and for the other players of this game. So these are first constraints of the problem, equality constraints. Now, since you have these probabilities, for instance, since the first configuration occurs with probability A and alpha, the outcome 65, you will obtain it with probability A times alpha. The outcome 40, you can obtain with probability A times beta, etc. And you can sum these values, and that gives you the expected outcome you're gonna win. So of course, what you want is to maximize outcome, but knowing that you're not the only one to make decisions, there's the other components. So maximizing, that means you want to find the best possible values for A, B, and C. And best possible, that means in particular, let's mention a few of them. So these values, A, B, C, have to be better than the one you would obtain if you fix, say, A to 1 and 0 to the others. So you have one inequality, one constraint. Okay, so it's also better than what you would obtain if you fix to value B, and it's also, you also want something better than what you would obtain if you fix to value C, probability 1. So you have 3 constraints, and you could, of course, fix to 1/3, 1/3, 1/3, these other things. But as it turns out, these 3 constraints are sufficient for this problem. And if we model these inequalities and same inequalities for the other agents of the problem, you model what they call the Nash equilibrium, which is that no player can increase its outcome by changing strategy in an unilateral way. So this is just an application we had a look at on an application of constraints on the continuous domains. But it was essentially to give you a first example. So that gives you an idea of what a constraint satisfaction problem is. You have a set of variables, alpha, b, c, etc. Each of them has an initial domain of values. Here it was a continuous domain. And they are subject to some constraints, of course. For instance, non-linear constraints, but you can have linear forms, and you can have discrete domains. So that's what we call the constraint satisfaction problem. Oh, yeah?
So A, B, and C and alpha, beta, you get to choose A, B, and C.
Yeah, and the other...
That's fine. So how does that show up in the statement of the problem?
it doesn't show up, actually.
Doesn't
Yeah.
show up.
No, actually, the weird thing in game theory is you have different agents, and each of them imposes some kind of constraint, which is I want my input to be maximal. And what I was showing was the constraint that just one player imposes, but actually both or maybe all of the players will impose that.
There are more constraints.
Yeah. Sorry, it's symmetric. The other player had exactly the symmetric constraints, and if you have 3 players, it's the same. Yeah, it's a weird form of constraints. It's an interesting problem for this reason, that you have different people putting constraints. So, constraint satisfaction problems, they have a number of established applications, industrial applications. For instance, in scheduling, resource allocation, configuration, and software and hardware verification. I like to think that maybe we don't have all of them yet, and maybe some new applications can arise. For instance, in cryptanalysis, obviously breaking keys and factoring, for instance, are constraint satisfaction problems in a way, although specific ones. And I don't expect constraint satisfaction tools to break RSA, these kind of things, but if you look at the state of the art in constraint satisfaction applied to these problems, what we can factor basically is numbers with like 10 or 15 digits, which is a bit ridiculous. I think the state of the art should be, if we do specific algorithms, and if we focus on integrating knowledge domain in these algorithms, I guess we can do better. And just for the challenge, it can be a nice application, I think. Well, I mentioned game theory, and more generally, there's a whole area of adversarial, what I call adversarial decision making, when you have just as you said, actually, you have your variables, but you also have to take into account the decisions of competitors or others, or decisions which do not depend on you. And that's an interesting question and a much more difficult problem, I guess, on which I will say a few words when I will talk on quantified constraints at some point in the talk. So far, it's a perspective, but I plan to work on it, and other people also. So that's for the applications, and here comes the theory diagram. Just to mention what kind of problem it is, of course, if you see my definition of constraint satisfaction problem, obviously we are NP hard in most cases. And I like this quotation of this artificial intelligence guy, David McAllister, which summarizes what he very, very roughly the kind of such procedures you have. He says, for P corresponds to the no such problems, and constraint satisfaction corresponds to NP, basically. And you have, of course, even more complex things, like if you want to do graph search and to explore transition systems, typically your NP space complete or even worse, actually, depending. But what I want to stress here is it's NP complete. And actually, if you think of your favorite NP complete problems, very, very often you can express them as a set of variables and a set of constraints on these variables. Many real-life problems, they can be modeled this way. Well, and just a few other favorite theorems I like to have in mind when doing this research is NP completeness is one good thing to know, but it's far from being what theory can tell you about these problems. And here are a few other things which are interesting to know. Some theorems which are not so famous in the area. Well, this one is actually quite well known, and many people are working on it. Schaeffer's theorem. Well, he classified a number of years ago the tractable constraints which can arise in when you have boolean domains. And actually, he proved that you only have 4 non-trivial possibilities. Either you have 2 SAT constraints, which are easy to solve. Either you have XOR SAT constraints, a horn, anti-horn SAT, or you are NP complete, as soon as you mix these constraints. Well, anyway, actually, it's proved. It's been proved a long time ago on Boolean domains, and people want to prove this, the extended conjecture for more general domains. But anyway. Oh, here's an interesting one, Fedgin's theorem, just on this connection on NP and constraint satisfaction. When you have a constraint modeling language, very often you wonder, can I model my problem or not with this language? And you don't have so many results on the expressiveness on these languages. And actually, if you look at the logic literature, you have some nice answers. And you have this theorem by Fedgin in the 70s, saying that, well, there exist logical languages which model exactly the problems in NP. And, well, the language is existential second-order logic. And actually, if you have a look, if you know a bit of this on this constraint modeling languages like OPL, which is, I think, the state of the art, it's striking that it's basically the same. It's syntactic notations for these kind of things, putting relations and having for all and these kind of things first-order quantifiers. It's very close. So basically, you can say that with OPL, you can express any NP problem. So if someone asks me, can I model my problem in OPL? I just ask, does it have short solutions? And if the answer is yes, I can find a way, hopefully. Oh, the 2 next theorems are related to the algorithms. Well, this one is not very well known in the field. This is very often when you do search algorithms, you wonder, should I start with exploring the left branch with 0, 0, 0, 0, or should I start with the right branch with 1, 1, 1? And if you ask the complexity theorist, he will answer, you have to do this by increasing order in Kolmogorov complexity, this particular measure introduced by Levin. And the reason you have to do it this way is because you have an optimality guarantee if you do this. You have the guarantee that if you have a solution, you're going to find it in a in a time which is at most polynomially higher than one you would have with any other search procedure. But polynomially actually can turn out to be big in these kind of things. So it's nice to know this theorem for it's nice theoretical result, but I'm still wondering if it can be applied. Computing this KT value is very difficult, of course. But anyway, one thing it proves, it's if you have problems which have solutions but still are difficult, that means they will be difficult by any possible algorithms you can imagine, because they have to be in particular difficult for this problem. And the last thing to mention on the algorithms is, well, a number of years ago, this guy called Hagen proved that if you want to prove that a formula has no solution, propositional formula, boolean constraints, if you would do a proof by resolution, this basic proof procedure, for some tautologies, for some unsatisfiable formulas, you have no proofs which are of size less than exponential. And does it have a consequence on the constraint solvers? Yes, because some other people prove that actually most of the basic algorithms we have in AI for proving unsatisfiability, they are in some sense a form of resolution. So that's a worrying thing. And one example of a constraint which is hard to do to solve, to prove unsatisfiable by any resolution-like method is simply this one. You have n minus n values, and they can take n minus 1 variables, and they have to be all different. And if you solve this using resolution, you're going to be strictly exponential with most search algorithms, most of our basic algorithms. So this explains when we have to use different methods on these kind of constraints when they occur, and they occur quite often, actually. So this was a broad introduction to the problem and to some favorite theoretical stuff. And now for yeah.
That last line again, it's like a contradiction.
A contradiction? Yeah, sorry. So this is a constraint satisfaction problem with no solution. Okay. But the thing is, the question is, it occurs very often that you have either problems or sub-problems with no solution. You want to prove it. You want the solver to prove it as fast as possible. And what this thing proves is for some unsatisfiable constraints, we can prove that actually the runtime is going to be strictly exponential, which is a bit worrying. So that's a contradiction. That's not satisfiable. But we want the solver to do better than this resolution search when we give him this kind of when we give it this kind of formulas. So just a state of the art on the algorithms. Well, if you ask me what can I do to solve constraints, there's a wide range of answers to this question. Because you have a number of methods from AI, logic, mathematical programming, and even if you look more broadly on DNA computing, statistical physics, some people recently have done works on with spins, these kind of things to solve constraint satisfaction problems. But roughly, if you consider the state of the art, you have, of course, two classes of techniques, the complete ones and the incomplete ones. Complete ones, they will guarantee you that they will find a solution if there's one, if they will guarantee you that you have known otherwise. And incomplete ones, things like local search, for instance, maybe they will use con flipping to try randomly. They don't give that much guarantees when you don't have solutions, but they can prove very effective when you have some. So it's a basic classification, and more specifically in this talk, I will consider branch and prune and these kind of complete methods, which do give guarantees when you don't have solutions. And the state of the art it's clear. I will just mention for Boolean constraints, finite-domain constraints, and numerical continuous domains. And the state of the art is clear, I think, especially on Boolean constraints, because you have one technique, one kind of solver which seems to be winning recently for the last 3-4 years at least. It's complete algorithms based on exhaustive search, backtracking. And if you have a look at what is inside these solvers, well, they do typically propagation and other stuff. But basically, the core is backtracking plus propagation. You have to enhance them both with close learning, nice strategies, restarts to make them more robust. But basically, it's backtracking, propagation. Quite routinely now, they solve quite big instances if you take real-life problems like hundreds of thousands of variables or even millions of variables in some model checking applications. I think the state of the art in finite domain is a bit less clear to me, but the state of the art solvers seem to be based on the same kind of thing, basically search plus propagation and heuristics. And you have a number of other techniques which are good to put into your solver, like global constraints. If you have some specific constraint which occurs in your application, you have to, it's good to have a specialized algorithm for it and to add it to your solver. And you have a number of techniques like detection of interchangeable values, symmetries, no good recording. But basically, same picture. Still, it's not so clear to me. I think integer programming techniques on linear constraints are quite competitive. There's no big winner among search techniques and integer programming, I think. Well, if you remember, in theory, we had constraints, and the variables were not ranging over a finite domain, but over a continuous domain like 0, 1. And if we have a look at the state of the art on these kind of constraints, well, the basic tool is interval arithmetics. You cannot enumerate through the real numbers. You cannot do a for loop on the real numbers, but you can have an interval and split it, and until reaching a satisfactory precision. That's the way these solvers work and the way they do search based on splitting. Once again, you have an important thing, which is propagation, and the key technique on these domains for, I don't know what is the explanation, but the best seems to be box consistency, a particular technique. And well, anyway, these solvers, so far, they don't scale up very well. I cannot. It's based on interval evaluation. So you know, when you have when each of the variables they have an interval value, you can evaluate it using different kind of techniques to have more or less tight evaluations. And box consistency, roughly speaking, if you have well, the search space, if you have 3 variables or more, it's going to be a box, right? And of course, you have to split it and until you find a small box which you think is close to a solution. But to reduce this box consistency, you just take some slices and evaluates the function on these slices. And and the criterion to see if you should reduce a phase set of the box or not is with evaluation. For instance, if you have f of x is equal to 0, and if the interval evaluation gives you 100 plus infinity, you know, okay, no solution here. So this is basically it's based on interval evaluation. Actually, I did my thesis in Nantes, and this technique essentially comes from there. This team was specialized into numerical constraints, these kind of things. Well, okay, I will speed up on this part. Okay, so the state of the art shows that propagation methods are important, even though they may not be sufficient per se, but at least the efficient solvers have to incorporate some kind of propagation. And propagation, in this part, I will describe first a number of variants on propagations depending on the domain. The idea of propagation basically is to make easy deductions. When you have this variable which has these kind of values, we do that, okay, so this variable cannot have this value, and these kind of things. So I will start by three kind of variants, and then generalize a bit, give you the general framework, and then more specialized algorithmic issues on which I give you personal contributions. Well, here is the most basic constraint propagation, and here we go back to the 60s with Davis, Putnam, Ludgerman, Loveland work and theorem proving. Propagation, when you have a Boolean clause, like a Horn clause, says you that well, if A is equal to 1 and B is equal to 1, then C has to be equal to 1. Let's not explore value 0 for C. That's basic thing. But actually, if we have a look at this Horn clause, this Horn clause writes non-A or non-B or C. So there's no reason to orientate it this way. Actually, we could read it in 3 different ways, the 3 following. And we have the same interpretation. But actually, if we can even avoid to explicitly write the implications. We just have the clause, and we just have to change the recipe we apply. And the recipe becomes, well, in this clause, if all literals but one are false, we know, since this clause has to be true, that we have to infer the remaining one. That gives you the same kind of reasoning. This is basic propagation. So this is multi-directional reasoning, and of course it's a particular form of resolution which I think is especially easy to see here. So this is the roots of our field and the kind of reasoning we do. Well, very often in applications you don't have only 2 values for each variable, but you can have finite domains which are more general. For instance, here is a constraint which impose some possible combinations between different variables, say. And how can we do propagation? But well, we can generalize a bit the rule I said before, and we can say that, well, if a value has no support means you have a line with a value in the other part of the table. If a value has no support, you can remove it. For instance, let's imagine that pink, we don't take pink. What are the consequences for the pants? Well, of course, blue has no support anymore in the shared variable, so we can remove blue. This is just an application of this rule. So this gives you a way to make easy deductions on the constraints, and just to see what are the respective advantages of this technique. You have search, which is exponential time, which is hard, but which is global and guaranteed to find solutions. And you have propagation, which reasons locally, constraint by constraint, which is effective but still is incomplete. It doesn't make all the deductions you have when you have a knowledge of the problem as a whole. Of course, you can mix the 2 of them. Typically, you do search and you interleave it with propagation. So I hope it was clear on finite domain. Just to mention how you can generalize it to numerical constraints. Well, let's have a look at these constraints, for instance. Here is a problem. What kind of deductions can we make at a low cost? Well, for instance, we have the second constraint, which says that y is the square of x. So y has to be positive, same for z. But now we have the second constraint saying that x has to be such that its square goes into the interval value for y. So we can reduce it once again. We can continue this way. I will maybe go a bit faster here. But just by taking every constraint and seeing which are the possible values on the bounds for each of them, you can do some kind of propagation, etc. And well, okay, if I go a bit faster here, we'll arrive to these intervals, if you believe me, after a few hundreds of steps, maybe a few steps at least. Basically, it's the same kind of thing. You take one constraint, you reason on it, and you see what you can deduce at a low cost. This is not box consistency. This is a simple propagation. Box consistency is a bit more costly to do, but a bit more. It prunes a bit more. Oh, here is the way we can do these reasonings as suggested before using interval arithmetics upwards and backwards. Just evaluating and doing it the same thing backwards. Okay, so maybe it's not so clear that the 3 techniques I suggested before are actually the same thing, but we have actually a general framework for these techniques. And the basic thing that these techniques do, they manipulate a search space. You have, for instance, a Cartesian product of domains or variables. And what you want is to reduce this thing because exploring it completely is going to be too costly. So you have your search algorithm. It's going to be complete, but at every node of this of the search tree, you want to reduce the boxes or the connotation or the domains or the search space as much as possible using efficient reasoning. This is what propagation does. So propagation algorithms, basically it's a function which takes a search space and which gives a search space which is smaller. And if we want to characterize these things algebraically, the important properties are the following. Well, you have to have a search space which is smaller or equal to the original one. You have to preserve all the solutions of the search space, of course. And it's good to have a monotonicity property which says that if you have a smaller search space, what you will obtain is going to be smaller than what you would have had initially. And very often the solvers we have, they are what we call idempotent, that you can apply the solver twice. It's the same that applying it once. So once you have done it once, you can forget about it. The nice thing is any algorithm which has these properties can be integrated into a constraint solver in quite an efficient way, because it will still be correct and you can still mix a number of these kind of functions, and you can compute a common fixed point. You can run all of these solvers until you have a box which you cannot, a search space, sorry, which you cannot reduce anymore. And the result is going to be unique, so that's a nice characterization. Okay, maybe I have to go faster for the 45 minutes. I started at 10, right? Maybe a bit later. So, yeah.
So I've got two different phi's from your previous slide.
Two different, sorry?
Two different
Two different phi's, yeah, sorry.
narrow.
Yeah, two different phi's, yeah.
So the result to the best would be the same as
No, sorry, the result of very often you have a number of phi's, and you're going to apply all of them, and what you want to have is the best reduction you can have. So you apply all of them, and what you will reach is a fixed point of all these phi functions. And the uniqueness theorem is just that whatever strategy you take, whether you apply phi 1 first and phi 1 2 or another, you're going to have the same result ultimately. That's a confluence result in a sense. Sorry?
not immediately obvious, because one might lead you into one part of the search.
Yeah,
and the other
well,
might lead you into a different one.
yeah, at first it might seem not completely obvious. It's obvious if you know the Nasser-Taskin theorem, these kind of things in logic, which are, yeah. Yeah?
So it finds the identity.
Yeah, you can. This definition is a bit loose. You could have potentially crazy things. Solvers doing nothing. A solver doing nothing is correct, because if you put it in a search procedure, it won't give you any pollution. You will have the result in the end, but of course it will take a while, because if you don't prune, but it's technically speaking is correct. Of course, what you want is the best compromise between, you want a solver which fulfills these definitions, but also which is effective at pruning and works well in practice, of course. That's the basic idea. Well, maybe I will skip this one, but basically I hope you can see that what I have suggested before basically fits into this framework, and the idea is that you reason constraint by constraint, and you remove values which are not solution locally to a constraint, say. Yeah, okay, I will skip strong consistency techniques too. So the nice thing about this framework is it's a bit loose. You can do whatever you want. You can take like 10 algorithms and make them work together. But the nice thing is with it, you can mix different methods in quite a nice way. For instance, even if in an asynchronous context, if you have a constraint network which is distributed over, let's say, 2 computers here, you have diamonds or the variables, and these things are the constraints. So of course you have some constraints which are shared between the 2 computers, the 2 sites. And the thing is, you can treat these communications just as phi operators. You have the guarantee that anyway you're going to have the same solution in the end. It doesn't say if it's the most efficient way of doing it, but at least you have a framework, a kind of generic algorithm to integrate a number of algorithms and potentially to make them run in a distributed setting. Okay, so now here are some, yeah.
So the drawing you saw, big intervals shrinking and shrinking and shrinking, which is all very nice if it actually happens. Is that always going to happen? Aren't you going to have
no.
couldn't you end up with very fragmented intervals that would be very hard to...
Fragmented, you mean if you take unions of interval, which is one possibility, but typically the solvers we use, they don't do in unions. Unions, it's nice because if you have non-convex things, you can have things which are a bit tighter. But typically, if you keep just an interval and if you split it afterwards, you have the same result. So basically, people try to keep intervals. But for the first part of your question, do we have any guarantees? No. I mean, typically, for any pruning technique I can think of, you can find solutions on which you have either on practice almost no pruning, or even provably for some cases, you can prove that your technique will not prune. So it's just in practice you make this. You hope that the solver is going to help you. In practice, for many problems it works, but there's no free lunch. I mean, you don't have any guarantees on these algorithms due to the complexity. Okay, so here I wanted to. There's been a lot of work on optimizing these propagation things, and of course, you want to propagate as fast as possible. And especially, most of the work has been related to binary constraints. So here is an example of a binary constraint. The edges connect compatible values. For instance, 2 is compatible with 6. And the question in the basic propagation algorithms for this kind of finite-domain constraints is, well, for instance, if we have value 7 disappearing because of another propagation, for instance, or because of search, which is going to decide to impose value 7, what consequences do we propagate on the right part, for instance? Well, we have to investigate, of course, these 3 values, and we have to remove value 4 because the only support it had was value 7, and we can keep value 9 and value 0 because actually we still have an edge connecting them to the constraint. Well, a classical algorithm to do that is basically as AC sex, which I would just suggest very briefly. You just put counters and basic algorithmics, nice algorithmic improvements. You have a counter which says for each value, which is the number of the first support in the next variable. And if you have a furthermore, you have a list for each variable of for each value of the values of the other constraint of which it is a support. So for instance, if you have value 4 disappearing, you just have to update the knowledge about value 4 and value 9 of y. And for value 4, for instance, you can just increase and inspect the constraint. And this one has no support of value higher than the 6 we had before. So we can remove it. And for value 9, we can just make 2 incrementations and see that, okay, we have a new support of lower value. So it's just an improvement which obtains the optimal complexity for this thing, which is md squared, where m is the number of constraints and d is the size of the domains. Well, these kind of things are quite ubiquitous in the literature. Many people have worked on optimizing these very specific propagation things. And for instance, well, you said this stuff in the distributed context. Well, if you have value x on one computer and value y on another computer, what you want to minimize very often is the messages between them, which cost much more than the internal computations. And here is a trick to do this. For instance, if you have value 2 disappearing, do you have to inform the other that the other constraint, which is a while ago of this deletion? No, because actually the only consequence would be that 6 has to increase has to update his knowledge, but 6 still has a support. So you can avoid communication here. Same for if value 9 then disappears, same because it has no consequences on the other variable. Well, now if it's, okay, if 7 disappears, now you have to do communication. And you have to inform of all the deletions you have done before. So this is an optimal way of doing communications in a distributed context. You have basically ND, I think, communications at most, where N is the number of variables and D number of values in each variable. Tell me if I'm wrong. Okay. Well, there's not been so much work on similar algorithmic improvements on intervals and numerical constraints, and this is some work I did in the beginning of my thesis, actually. So one technique, basic interval propagation, is a good tool to have on the interval constraint, but very often it's not enough. You have to do something a bit stronger, like box consistency. Another technique is Lamb's so-called KB consistency. And here is the way it works. It's, you have this basic function phi, which if you give it a box, it will reduce it, but keeping all the solutions. And Lamb's technique is, well, you have a box which is too big, so you can just take parts of it and run the solver on it, and you obtain something smaller. If this thing smaller is empty, you can just forget about these values. This is what Lamb's KB consistency does. Well, the basic algorithms for it in the literature were a bit doing things as they come. And actually, just one contribution of mine, you see in the Ishkai paper, is well, you can just do better using a minimum of storage and a minimum of clever algorithmics. You can just memorize these boxes, and you can handle a bit carefully the reductions, avoid sometimes to call the solver on the phase set when it's not needed, and when it's absolutely needed, you can just do clever intersections. That gives you a better complexity bound, which is a bit costly though still, but MDN2 square, well, M is the number of constraints, D is the size of the domain, and N is the number of variables. That was an improvement by N with, compared to the original algorithm that Lom proposed. So it was MD2N2. There was an additional factor which could actually be avoided, leading to practical improvements. Okay, so it was a big picture on the propagation things. Now, most propagation techniques, typically you deal with, you have the variables and you want to prune them, but you have the assumption that all the variables, they kind of belong to you, contrary to the game theoretic context. So one thing I did during my thesis, and actually it was the main part, was to investigate, is it still possible to do propagation when you have constraints with a more general form, like especially quantified constraints. And here is why I was interested in quantifiers. So quantifiers, once again, that's the adversarial setting. You have many variables, but you don't have the possibility to choose for any variables because some belong to an opponent. If you chess, some variables are given by the choices made by the opponent, but you don't choose what he does in practice, unfortunately. So quantifiers are just a convenient way to model most of these situations. So the adversarial setting is, okay, some parameters do not represent the choice, your choice, but over the choices of an opponent or of a fictitious opponent. Just nature. You have a variable which is sales, but you don't know the sales of the month of January. You just can approximate it, hopefully. For instance, you have a stock. The stock at time t plus 1 depends on the stock at time t, but you have to add the production and you have to deduce the sales. Typically, you can choose the production, you cannot choose the sales. And typically, if you want to do safe reasoning on this kind of problems, you want to some kind of for all quantifier. You want something which guarantees that for all sales, whatever happens in the month of January, I'm going to be able to have a non-empty stock, for instance, these kind of things. Well, you can have either traditional for-all quantifiers, or you can have some randomized forms. Like some people use this R as a stochastic version of the. Oh, okay. Yeah, the application may be safer. Okay, so just to skip. Okay, so basically, just what I did in my thesis was to define, to generalize this notion of R consistency to this context of quantified constraint. I think it's the good generalization that we proposed ultimately. Okay, so that's it for propagation. So a number of applications and perspectives. We spoke both on the perspectives for improving these methods and make them more effective and more robust. And some, very briefly, to suggest some applications to verification on which some of you might be more expert than me. So cooperation, if you remember the beginning of the talk, I mentioned something that propagation is a nice technique. It's very useful in practice. Still, there are some problems which have no solution, and propagation just cannot prove it. And it's not a small question. It's not something you cannot tune the propagation. Basically, it's not the right way of doing it, just because it's not the right proof system in a sense. It results from proof complexity. So this proves that an important way of making solvers more scalable and more robust is to integrate them and to mix with other techniques. And here I just wanted to, well, maybe just told by another view. It's actually integration, cooperation. This is well known. It is a well-studied and active field in literature. You have now an international symposium, CPAIOR, on the integration of constraint programming, artificial intelligence, operations research technique. And global constraint, which I mentioned, are a form of such integration. If you have a problem-specific algorithm, you can plug it into a phi function in a way. So this is, there's a lot of work on these things, and there's still a lot of work to do. But just one thing I wanted to mention, which is a theoretical point that I didn't see mentioned in the literature, is when you have two solvers, is it worth mixing them or not? And it's a question that on which theory can help you having some reasoning. Well, just maybe to speed up here, the kind of results we have in a field called proof complexity is if you take techniques like BDD, binary decision diagrams, and resolution, people have proved that they cannot give short proofs of unsatisfiability for the same class of formula. Sorry. So, for instance, you have these all diff constraints on which resolution is not effective. Well, it turns out that for the same kind of problems of unsatisfiable constraints, you can handle them with BDD. So you can prove here that you have an improvement, that you have a more robust solver if you mix the two techniques. What I was starting to do is kind of a classification of the techniques. You can prove that some techniques are not comparable. You can prove that some techniques are more general than others. I think it's a nice reflection to have when you do cooperation. So maybe just a few words now on verification. So verification, well, this isn't exactly verification. Verification, the basic idea is to use constraints as a compact way of exploring paths in transition systems, which are typically described in a concise language, but actually are much bigger than their description. Here is an example of, actually it would be like more a planning problem where you have some variables describing the key, the door, and etc. And you have some rules between two states of the two configurations. For instance, initially you are inside the building, you have the key in the end, and the door is locked. And you want to go to the state where you are outside with the key in the hand and the door is locked safely. You can express the transition between two states as constraints. Okay, this is a graph you would obtain. This is the path leading from the initial to the final state. Well, there's been a lot of work, I think, on both the planning and the model checking verification community to use constraint solvers to express the existence of paths. This is what they call the planning as satisfiability and bounded model checking. So very roughly, the basic idea is you want a path of length k. And since you have the constraint between two configurations, you have the vector of variables for configuration x1, the vector of variables for configuration x2, you have the constraint between them. Just by duplicating the constraint, you have a constraint satisfaction problem. It's bounded, but still, this way you can cope with the non-determinism and have a way to explore these search spaces in a bounded way. Actually, one problem is you have to bound. If you use quantified constraints, there's a trick to express things in a more concise way, so that with a small number of constraints you can express paths of a much bigger scope. Only problem is so far the quantified solvers are not as effective as the non-quantified ones. So actually, there's no proof it pays so far. Well, I mentioned an example which was in the kind of planning spirit where you have with this door, but actually in most applications you don't have the graph described directly as constraints between two states. Very often you have concurrent systems, distributed systems, and actually the transition systems is just the possible transitions between the communications between the different agents. So we've been working a bit in Rome on the web services settings and on the verification of web services. And kind of things you have is you model your system using some process algebraic or automator-based notation. And of course, if you have this, you can use the operational semantics to express the possible transitions, and you can do some verification on the possible executions of the system to prove things like absence of deadlock, some properties. You have this setting with temporal logic model checking, and you have these questions of equivalence, compatibility, and absence of unspecified receptions. All these very nice things to check on the system. I didn't work specifically on the algorithms because we had no specialist in Rome on these issues, and actually you need a specialist if you really want to plug your hands into the solver and to put constraints on them. We've been using these things a bit. Okay, so that was a bit brief on some parts. Just to conclude, and I think it's time for that. A few concluding words in the optimistic conclusion. Well, propagation is not a new technique. It goes back to work in the 60s with Davis and Putnam. But there's still some exciting work to do on propagation methods, especially in the distributed setting, which is not so developed, if I'm correct. And one kind of applications which seem to be promising is the adversarial methods, on which it seems to be quite new and it seems to have quite some applications. Maybe some of the applications can be explored. Nevertheless, propagation alone has some limits, and of course, one very active and very promising thing is to do cooperation with other methods. I didn't mention things like cooperation between complete and incomplete methods. That's a nice way to enhance the effectiveness of a solver, typically. But potentially, you have a wide range of techniques you can hope to make cooperate in an effective way. So, okay, I hope I'm not too late. Thank you. Okay.